When you have been introduced to the differentiability of functions in one variable, then you were also introduced to the notion of chain rule. So briefly speaking, what is chain rule? So this tells us how do we differentiate composition of two differentiable functions f and g. So let me recall this briefly. So suppose d and e are subsets of R, and suppose f is a function from d to R and g is a function from e to R. And suppose that it is satisfied that f maps d into e. So f of d is a subset of e. And suppose that c is an interior point of d and fc is an interior point of e. So as such, what it means is that we are now allowed to talk about differentiability of f at c and g at f of c. So suppose that f is differentiable at the point c and g is differentiable at the point f of c. So then we claim, or we have seen in our one variable calculus, that then the function g composed f is differentiable at the point c that we originally started with, and also we got this very nice formula that g composite f, and if I take its derivative at the point c, then it is nothing but the following: g prime f of c times f prime c. Now we are going to see its analog, which is called the chain rule for multivariable differentiable functions. And I will tell you about three authors of chain rules in the case of multivariable functions. But here, as I have said, during this course we will always restrict our attention to functions of two variables. Okay, so as always, we have a domain D in R2, as we are talking about functions in two variables x0, y0, and interior point of D, because we are going to, after all, talk about differentiability of a function which is f, a real valued function on the subset D. And suppose that this function is differentiable at the point x0, y0. So now here comes the first avatar of chain rule. So what does it say? So it says that suppose E is a subset of R such that f of d is contained in E, something that we have seen before in single variable calculus. And now we had a point x0, y0 which was an interior point of D, and suppose that I call f of x0, y0 to be equal to z0, and since we are again going to talk about differentiability of another function on E, we must take z0 to be an interior point of E. And suppose g is a real valued function on E. So note that E is a subset of R. So g is essentially a function in single variable. So g is a differentiable function at the point z0. z0 is f of x0, y0. Then our claim is the composite of these two functions, g composite f, is differentiable at the point x0, y0. So if I call this composition as h, then I could easily compute the total derivative by computing what is the partial derivative of h with respect to x at the point x0, y0, and y partial derivative of h with respect to y at the point x0, y0. And these are given by some very simple expression, first one being g prime z0 times fx. So this is the partial derivative of f with respect to x at the point x0, y0, and hy is simply given by g prime z0 times fy x0, y0. So we can write this in a very nice way. All the expressions are captured in this very nice concrete or compact expression. So it says that the gradient of g composite f, which is the total derivative of g composite f at the point x0, y0, so this is given by g prime z0, which is a constant, which is a scalar, times gradient of f at the point x0, y0. So let us now look at pictorially what is going on. And so what we had is that D is a subset of R2, so we have taken D a subset of R2. So I have a map small f from D to R. So this is our real line, one of those, and suppose that E is a subset of R. So E is suppose given by this region. So pictures are mostly misleading. You might get an idea that E is an interval, but it is not necessarily so. All we have E is a subset of C, and then we have a function G, which is whose codomain is R. So what is given to us is that we have a point x0 y0 here. So under f, this gets mapped to a point here, which we call z0. We said that our hypothesis said that f is differentiable at this point, g is differentiable at this point, and both these points are of course interior points. And our conclusion said that if I take the composition g composite f, which I called h, this function is also differentiable at this interior point x0 y0 of t. And also we have computed, or we have at least told you, what is the corresponding total derivative of this function h, which is g composite f. So let me now give you an example. So very nice example to start with. So f is a function from R2 to R given by fxy is equal to xy, and g is a function from R to R which is given by gz equal to sin z. We are going to, so what is our g composite f? So first of all, our domains are as follows. So D is equal to R2 and E is equal to whole of R. So we do not really need to check otherwise whether the points that we are going to take is an interior point or not, because any point in R2 is going to be an interior point on R2, and any point in E R, which is R here, is going to be an interior point in R. So we do not need to really bother about those kind of technicalities here. So can we compute the function h of xy, which is given by g composite f xy? So of course, so what is g composite f of xy? This is simply g of f of xy, and f of xy is nothing but xy, so this is xy, and this is gonna be sine xy. So this is what we have got here, and our chain rule says that hx. So first of all, we know that this function, if we have seen that this function is differentiable, and we have also seen that sin z, the sine function, is differentiable. The chain rule says that if I pick up a point x0 y0 in R2, if I pick up a point x0 y0 in R2, the function f is going to be differentiable at this point x0 y0, and also if I take z0 to be equal to f of x0 y0, so then this point is g is going to be differentiable at this point z0. So note that z0 is nothing but the real number x0 times y0. Our chain rule says hx x0 y0 is given by g prime z0 times fx x0 y0. If you carefully evaluate this will come down to cos of x0 y0 times y0. Similarly, we can compute hy of x0 y0. This turns out to be equal to cos of x0 y0 times x0. Consequently, what we get is the following. The gradient of h at the point x0 y0 is equal to cos of x0 y0 times the tuple y0 comma x0. So here I had shown you that this function f is differentiable at the point x0 y0, but I am sure that you can do it on your own. Let us go forward to our second avatar of chain rule. So what do we have? This is a bit complicated than what we had before, but it is not tough either. So here we have this fixed assumption that D is a subset of R, x0, y0 is an interior point of D, and f is a real valued function on D. So this is a function in two variables. So this is always given. So now what we have is that E is a subset of R. So E is a subset of R, and suppose that T0 is an interior point of E. So that somehow gives us the clue that we are going to talk about a differentiable function on E, or at least a function on E which is differentiable at the point T0. Okay, so let xy be two differentiable functions too. So two functions on E, two real valued functions on E which are differentiable at T0. So since E is a subset of R, E, x and y, these are just single variable functions in one variable, let's say T. So if xt comma yt, this tuple belongs to D for all t in E, and if I can denote xt0 comma yt0 simply as x0 y0, then we claim that the function that we will get this way, phi t, defined as f of xt yt for t belonging to E, this function is going to be differentiable at the point t0. So let me explain this, what we are saying. So I have to begin with a subset of R which I call E. Again, pictures are misleading. Do not get a feeling that the C has to be an interval. It can be any subset of R. So I have two maps. X and Y. So let's say a white map which is X and a red map which is Y. I have an interior point here T0, and this maps X and Y. These are differentiable at the point T0. So then I can combine these two maps as follows. So this gives rise to a map to R2, which is given by xt0 comma yt0. I hope this is clear. So t0, this gives an image x of t0. y0, this gives an image y of t0. I just write out this tuple. This will be an element of R2. All we know about this x and y is the following, that x and y are differentiable at the point t0. Now if it so happens that if I call this map psi, okay, let me call this map which maps t to xt yt to be psi. So suppose that the psi maps everything inside D to be inside R region D, which was a subset of R2 that we initially started with. Recall that we do always have a function f that is always constant. I mean, the function is not constant, but the assumption is constant that we have a function from D to R. Okay, so we have this map psi of t is given by xt yt, and for all t in E, we have that this elements is a subset of t. Then the composition of this function f and psi. F composite psi makes sense. And we can ask whether this composition f composite psi, which I will show you that we have called phi in this context, so whether this function is differentiable or not. So as such, you can see that the composition of this function is a single variable function from E to R, and E is of course a subset of R. So I hope that this makes things a little bit clearer. So now let me see what we have. So if xt yt, these tuples belong to D for all t in E, and xt 0 yt0, so why don't we say that this is an interior point? Okay, it is not needed because this x0 y0 was assumed to be an interior point. So t0 we chose a point to be such that the image of this map, which I call psi in the pictures, is equal to x0 y0. Then the function phi t is equal to, which is defined as f of xt yt for t in E is differentiable at the point t0. Moreover, the derivative of phi at the point t0 is given by fx at the point x0 y0 times x prime t0. So x prime of t0 is nothing but dx dt at the point t0. So fy of x0 y0 times y prime t0. Okay, so this expression can be written as dot product of two tuples. So the first one being the gradient of f at the point x0 y0, which comes from here, and the second tuple is x prime t0 y prime t0. So now let me look at an example to illustrate this to you. So suppose that f is a function from R2 to R, if xy is given by x square plus y square. We have seen various properties of this functions. So for example, this is differentiable, etc, etc. So xy are two maps from R to R. So xt is given by e to the power t exponential function, and yt is equal to sin t. So these are functions in one variable, and we have seen that these functions are differentiable in your calculus 1 course. And if you want to really evaluate what is the composition of these functions that we have just talked about, so this is f of xt comma yt. So this is the kind of functions that we were talking about, f of xt comma yt, composition of the maps that we illustrated in the pictures. So f of xt yt is f of e to the power t sin t. So these are the values of xt and yt, and if I use this formula, what is f of xy, then this turns out to be equal to e to the power 2t plus sin 2t. The fact is that we can compute the derivative of this function with respect to t easily, and at a point t0 this turns out to be 2 e to the power 2 t0 plus 2 e to the power 2 t0 plus 2 sin t0 cos t0. So this will be a very good point where we can double check if our consequence of chain rule is going to be correct. So we have these functions. So we have this maps R to R2 given by xy, namely I pick a point t0. This maps us to xt0 yt0 in R2, and this is an interior point, we know, because this domain is R2 and any point inside this is an interior point. And suppose that I have this function f, which is given always, and this function is x square plus y square, and x, y are given as above. Xt is e to the power t, yt is sin t, and all I need to compute is this dot product. So we want to compute what is fx at x0, fy at y0. These are very easy to compute. And it's also very easy to compute what is x prime at t0, y prime at t0. We put in all this information and we get exactly the same thing that we have just seen using our one variable calculus. Now let us go to our third avatar. So what does it say? So as you can see that the first line is persisting here also. So D is a subset of R2, x0 y0 is an interior point of D, and suppose that f is a differentiable function, f is a function which is differentiable at the point x0 y0. So again, this is a bit complicated but not very tough. So E is a subset of R2. Previously we had E was a subset of R, and suppose that U0 V0 is an interior point of E. So then you may think that we are going to talk about a function or functions which are differentiable at the point u0 v0. So this is why we have made this assumption, interior point. You are right, we are going to talk about two such functions, x and y, like before. But of course note that these functions are not anymore functions in one variable, but they are functions in two variables, because E is a subset of R2. So these functions are differentiable at the point u0 v0. And also we have the condition that if I take uv from E, then x uv y uv is an element of D. So this is not really a subset. This belongs to D. So as such, what we are saying is that so if we take this function, let's say xy from E to R2, then xy maps E inside D. And of course we do need this assumption that u0 v0, where this point was chosen in such a way such that the image of this point under this map xy is going to be x0 y0. This was an interior point, and we know that f was differentiable at this point. So we are going to construct a function, let me say script f, from E to R, and what is the script f? So script f of uv is f of x uv y uv, and we are going to say that this function is differentiable at u0 v0. So let me again try to illustrate this pictorially to you so that you will remember. So I have E, I have two real valued function on E. So how are they? So I have one white map which I have called x, so which takes a point uv to xuv, a real number. I have a red map which is denoted by y. This takes a point uv to yuv, so I can combine this together to get an element of R2, and I take all such collections, and in this way our claim is that if I take any point from here, this falls here inside D. So if I call this map phi, which I have called xy before, so if I call this phi, so phi of E, so our condition is that phi of E is a subset of D. And then what we will do is that we will take the composition of phi and f, and our claim is that the composition is differentiable at the point u0 v0. So this is all the statement says, and the statement also tells us how do we evaluate. The statement also tells us how do we evaluate the total derivative. So here are some typos which I of course have to correct. So it says that script f suffix u of u0 v0 is nothing but fx x0 y0 times xu u0 v0 plus fy x0 y0 times yu u0 v0. So here there are also some typos. So informally speaking, so this is del script f del u is equal to del small f del x times del x del u del small f del y times del y del u, and here also it is del script f del u del small f del x. So this is del f del v, and this turns out to be equal to del small f del x del v, and del small f del y times del y del v. So this can also be written as so this gradient is expressed in this way in terms of dot products, and we are not going to discuss it deeply. So just the formula written somewhat clearly turns out to be as follows: del f del u is del small f del x del u, as you like to write it in your one variable calculus, but you do remember that these points are different, and this is del f del y times del y del u. On the other hand, del f del v, you just replace u by v here, del f del x del v plus del f del y times del y del v. Now let me just illustrate this after with an example. So as before, I have taken this function f of xy from r2 to r as x square plus y square. So this is x square plus y square, and I have this white map and the green map. So the white map is given by u square minus v square from r2 to r, and y of uv is given by 2uv. So you can actually compute this composition, and what it turns out to be equal to this quantity. So u comma v gets mapped to u square minus v square whole square plus 2uv whole square, and so this is not this f, this is script f. Script f of uv is equal to u square minus v square whole square plus 2uv whole square. This is a very familiar form from your high school algebra, and this turns out to be equal to u to the power 4 plus 2u square v square plus v to the power 4. Now if we want to use chain rule, so this is of course a script f, but in this example it doesn't matter, but let me persist with my notation, and you can easily check that the script fu turns out to be equal to 4 u naught times u naught square plus v naught square. And of course, and similarly, if you want to go through all the calculation, if v will turn out to be equal to 4 v naught times u naught square plus v naught square. Of course, if you have this expression for f, that f of uv is equal to this expression, then you can by hand compute the values fu u naught v naught. So this is script fu u naught v naught, this is script fe u naught v naught, and you can see that the expression that you get by both the calculations are the same. So I hope that I have made things clear with respect to the chain rule. Let me just spend a couple of minutes summarizing what we have done. So here let me summarize what we have done just now. So suppose the first of that is as follows. So suppose I have a map from D to E. E is a subset of R. This E is a subset of R, and I have a map from E to R. So this map comes from single variable calculus, and this map comes from multivariable calculus. And with all the nice conditions being satisfied, if f is differentiable at this point, g is differentiable at this point, which is the image of this point particularly speaking, then the composition of these two maps is going to be differentiable at the point x0 y0, and the total derivative can be computed very easily in terms of the partial derivatives of the composition. The second of third was somewhat more complicated. So here we started with a subset E of R. Again, I want to stress for the final time that the pictures are in general misleading, and there is no reason to think that E is an interval. E can be any subset. All we need is that the point that we have chosen t0 is an interior point of E. So I have a map psi which comes from taking a white map which I call x, which is a real valued function on E, and a red real valued function on E which I have called y. So I can combine these two by writing the image of this as the tuple of images of these two maps. So as such, what is the image? So if I take a point t, and so then psi of t is going to be x of t comma y of t. So our condition was that this map psi thus constructed takes this region inside D. So psi of E is contained inside D, and also we have been given with this function throughout, a differentiable function, a function if from D to R, which is differentiable at the point x0 y0. So note that t0 gets mapped to x0 y0 here. Then our claim, then our conclusion from the chain rule is that the composition of these two maps is differentiable at the point t0, and of course the derivative of this real valued function, which is the composition of these two maps, can be computed in this manner. Finally, the third after, so we have E as a subset of R2. So we have two maps again, two real valued functions. So one white, which I call x, one red, which I have called y. Similarly, I can construct a psi, which is given by psi of uv as x uv, y uv. I have a function f, and so I take u naught v naught here, and I already were given with the point x0 y0. The condition was that u0 v0 gets mapped here at x0 y0, and if I now take the composition of these two maps, then the resultant map is differentiable here, provided the map psi takes E inside D. So this map is differentiable at the point u0 v0, and the total derivative of the composition can be computed in a rather easy way. So this is all about chain rule. We will talk more about multivariable calculus in our upcoming videos.